Welcome to a lesson with Dr. Pal. In this video, we're going to compute the derivative function using a limit of f of x equals square root of quantity x minus 2, but this time we are going to use the h strategy. Last video we used the a strategy. Here we'll use the h strategy. What's the difference? Well, first of all, we start the same. We have a point. We're heading toward the point x, and we want to find the slope of the tangent line just at x. And the y value will be x minus 2. Then instead of having another point with an a in it, we have a point with an x plus h, where h is like the little bit that we're going away from x. So h is the run. So that's what we're using with the h strategy. And then what we do is we plug in x plus h into the function itself. So then we have x plus h quantity and then minus 2. All right. And then we want to compute the rise of a run. So when we compute the rise of a run, notice in the run, we have the run is just h, because x plus h minus x is just h, and that's how we chose h to begin with. So in our difference quotient, we'll have an h, difference quotient meaning the average rate of change we're computing between these 2 points. And we subtract these two. Square root of quantity x plus h minus 2 minus. Now if you compare the different fractions that you get using the a strategy, we don't have an extra thing to add inside under the square root, but we have an extra thing down below. So you can take your pick which one you prefer, because I mean it's really preference here. H approaches 0. Notice that before we have a is approaching x, because these two, so think these two x values are getting close together, but if they're getting close together, that means h in this case is going to 0. H is the run. The run is going to 0, the rise of a run. Okay, so now we proceed similarly, thinking of difference of two squares. And so I can write out an x plus h, and I'll dispense with that set of parentheses right there, that pair of parentheses. So minus 2, and I'll put a plus x minus 2 to the top and bottom. And what we end up getting is on the top we have the first guy squared, so x plus h minus 2. That just means the square root's gotten rid of. And the second guy is also squared, but keep it in parentheses here. Minus x minus 2, that's because this negative will apply to the whole thing. We're subtracting off all over h, and then the bottom we have this x plus h minus 2 plus square root of x minus 2. Okay, and we're taking a limit as h approaches 0. Now, notice this is really nice. I see an x minus 2 here, and I see an x minus 2 here. See, x minus 2 and an x minus 2, but this one is subtracted. So it's like you're subtracting away what you had here. You had an x minus 2, but you're subtracting it out. I mean, when you distribute this negative, it'd be x minus x and negative 2 plus 2. Really, all those guys are gone. So you only have an h on the top, an h times 1. You could think of it as h times 1, if you will, which when we cancel, divide out both top and bottom by h, we'll be left with the 1 on the top. Now we can now notice that we don't have a domain issue, so we can throw in 0 for h, keeping in mind that h is the variable of this limit. X is a constant with respect to the limit. H is what's changing here. X is like a fixed constant point temporarily, as we're thinking about the slope right at the x, at one particular x value. So we're kind of holding this constant in this limit. H is what's changing. So we can throw in 0 for h here, and you end up getting 1 over square root of x minus 2 plus square root of x minus 2. And that becomes 1 over 2 root x minus 2. and we just computed the derivative function. That's what the derivative function will be equal to. And we used the H strategy. Thanks for watching.